This question is on Newton's second law. So let's take a look at the acceleration and forward pulling force graph. So looking at this graph, you notice that the forward pulling force needs to be at 0.5 newtons before the box can start to speed up and start to accelerate. So this matches with what the paragraph says, that there is actually a frictional force of 0.5 newtons. Therefore, if the frictional force acting on the box is 0.5 newton, you need to pull it with a force that can overcome the friction that is bigger than 0.5 newtons. Only when you can do that, then the box can start moving. So this is actually what is happening in the scenario here. Therefore, for part A, the box, the forward pulling force needs to be more than 0.5 newtons to overcome the frictional force. Then there can be a net force that makes the box accelerate or to speed up from rest. Now for part B, you are to calculate the value of the mass of the box. It's a standard question. We need to use second law and we need to sum up all the forces using a vector addition. So let's take a look at the answer. For calculation on Newton's second law, always remember to define which vector direction is positive. So I always like to take the forward direction to be positive. I've drawn an arrow in my workings to represent that. Make sure you have that too. With that, I'll just choose a random point on the graph. So the point that I've chosen is 2.5 newtons over here. So when the forward pulling force is 2.5 newtons, I realize that the acceleration is 1 meter per second square. So I written it down here. I have plugged this 1 meter per second square into the acceleration value. Mass is my unknown that I want to find. And the standard way of solving Newton's second law is always to sum up all the forces. So over here, I'm summing out all the forces. I have my forward pulling force, and also I have my frictional force. Take note that whilst I sum out all the forces, some of the forces will be positive and some of the forces will be negative. So in this case, the frictional force is negative 0.5 newton because it's pulling it towards the back, which is a negative direction. So be very careful about these positive signs and negative signs, because forces are vectors after all. So if you can set out the equation correctly, you should be able to get the correct answer over here, where the mass of the box is actually 2 kilogram. Okay, the units is wrong. It's 2 kilogram. It's not 2 meter per second squared. So in part C, we are to determine the speed at 3 seconds when the force is held constant at 2 newton. So at 2 newton, with a pulling force of 2 newton, from the graph, you can see that the acceleration value is 0.75 meter per second squared. So I've written it down, and with the acceleration value known, you can use the kinematics equation, acceleration equation, to figure out what is the final velocity or the final speed. So using the equation, A equals to v minus u over t, final velocity minus initial velocity over time. You can rearrange the equation to get what is the final velocity, and the final speed is just the value of the final velocity. That's how we can get 2.25 meter per second. Now in part 2, at 3 seconds, you are told that this forward pulling force is now reduced to 0.5 newtons. Notice that the forward pulling force now matches the frictional force, and with this you can see that the forces are balanced. When the forces are balanced, by Newton's second law, there will not be any net force, there wouldn't be any acceleration, and this tallies with what the graph tells us too. The graph tells us that when the forward pulling force is 0.5 Newton, the acceleration of the object is 0. It doesn't speed up, nor does it slow down. So for part 2, the object or the box will just move at a constant velocity, and the constant velocity follows that at 3 seconds, which is 2.25 meter per second. In part D, we need to apply Newton's third law, and there is this very common mistake and misconception that all of us would have made one point or another in our learning. So the question actually tells you this mistake. We look at the forward pulling force P, we look at the frictional force 0.5 Newton, we see that these two forces can be equal and they are definitely opposite. So the equal opposite forces can appear, and we might mistake these two forces as paired forces, which is wrong, because being equal and opposite is just two of the three criteria needed for these forces to be paired forces. The third criteria is paired force always acts on two different objects, not one. Alright, so if you look at P and 0.5 Newton's frictional force, these two forces, whilst they are equal and opposite, they act on the same object, just one object. So these two forces are not paired forces. So we are to find out what is the correct paired force to P, and I will reshare the technique that I've taught you all in class on how to find paired forces by Newton's third law. Okay, so first up, let's focus on the force that we want to analyze, which is force P. So I've drawn force P on a diagram, and it is super important for you to label this force with the objects involved. This is critical for Newton's third law paired forces question. So every force, there are two objects involved. An object that the force acts on, and another object that causes the force. So in this case, P is a pulling force caused by a student acting on the box, pulling on the box. So I make sure to label it this way. Please follow the way to label your forces. Second step, we will use the equal and opposite phrase in Newton's third law. Do draw a reverse arrow. So I'll just draw a reverse arrow, noting that this paired force must be equal in value, which is the vector, the arrow must be of the same length, and opposite in direction. Lastly, the third step allows you to find the object. So the third step is simply just to look at the two objects that you have written, just do a swap in the objects. So just now, the pulling force is by student on box. Right now, I do a swap, and this pulling force, this paired force must be by box on student. Just simply do a swap. And once you have labeled this properly, you realize that this paired force is a force that is acting on the student as what you have written. So therefore, you can join the student. So with this, you are able to identify what is the paired force very, very easily, and also what is the object that this paired force acts on.